This is the 8th part of a series of many approximately 10-minute lectures about parametric curves and also understanding parametric curves using the computer program Mathematica. In parts 1 through 7, we've been focusing on modeling straight line motion at a constant speed. In this video, we throw you a curveball, and now we're going to model straight line motion at a non-constant speed. The speed is going to change. In future videos, we'll also model curved motion, both at constant and non-constant speeds. These videos are aimed at students from pre-calculus through multivariable calculus, as well as physics students, both in high school and college. And we are ultimately trying to develop calculus tools to understand these curves. And even if you're in pre-calculus, I would encourage you to stick with this to try to help you understand what calculus is for. And I want to illustrate a non-constant speed curve at the beginning of this video by showing you the butterfly curve. I showed this back in part 0, which was my introductory video. Here Mathematica is tracing out a curve that looks like a butterfly. It's doing it in kind of a non-smooth, herky-jerky way. Ideally, it would be tracing it in a very smooth way. Calculus is designed to help us answer questions about the motion that we see here as far as the drawing goes. For example, we could try to answer the question of how far did the curve go? Pretend the distance units are in meters or something. You can figure out use calculus to figure out how far the curve went. What is the length of the curve, the arc length? We could also try to figure out where is the motion fastest. We can use calculus tools to do that. We can figure out where is the curve sharper. Near these peaks, it's sharper than near the places where it looks almost straight. It's curving more near the peaks there. Those are the tools that we're trying to develop to help us understand that. Here's been our main example. We've been using parametric equations and in fact linear functions to try to model the motion of a person traveling from the point 2, -1 to the point -1,3 in 1 second at a constant speed. And in the last video we figured out how far the person traveled and what the person's constant speed was. It should make sense that linear functions like these should help you do that. This f of t gives you the first coordinate, the x coordinate of the point as t changes. The g of t gives you the y coordinate of the point as t changes, and they are linear functions. If you combine them into one point-valued function called c of t, that's just another way of thinking about it that is sometimes useful. Now we want to, as far as the answers go to those questions, we use the Pythagorean theorem to figure out that the distance traveled by the person was 5 meters as they go from 2, -1 to the point -1,3. And since we assume they went at a constant speed, we can figure out that speed as distance divided by time and get 5 meters per second. Now we want to consider another foundational example, modeling straight line motion at a non-constant speed. And basically what you see here, everything is the same as the last question, except I've emphasized now we're doing it at a non-constant speed, and we're going to calculate the person's average speed instead of their actual speed the whole time. Their speed is changing, so we have to calculate an average. As far as these questions go, the answers are pretty easy. The answers for the distance is still 5 meters because we're still starting at the same point and ending at the same point along a straight line. I guess I never said that here, huh? Okay. Along a straight line. And the average speed is still going to be calculated as distance divided by time. But you would interpret it differently. You'd still get 5 meters per second, but that's not the speed the whole time. That's just the average speed. And we'll try to ultimately understand what that means too. But how about this first thing? How can we model straight line motion at a non-constant speed? Well, first of all, without actually knowing what the motion is, you can't get an exact answer. In fact, there would be a unique exact answer for any particular given motion, but since I don't know what that motion is, there's really going to be infinitely many different answers, infinitely different many ways that I could try to model this kind of non-constant speed motion. And for the purposes of this video, what I'm going to do is I'm going to take the manipulate code right here, and I'm going to copy and paste it down here, and I'm just going to make some changes to this. Okay, and we want to try to understand these changes. What I'm going to do is I'm going to replace the input for the C function, which effectively does also mean changing the input for the f and g function, since C of t is a point-valued function whose first coordinate is f of t and whose second coordinate is g of t. I'm going to take that input and I'm going to change it. Instead of a t, I'm going to have something else. Now, there are infinitely many choices that I could make here. I also want it to be a quantity, a function of t really, that I'm going to plug into the C function, whose output at t equals 0 is 0, and whose output at t equals 1 is 1. Why? Because that's still going to give us something that starts at the right point, ends at the right point over 1 second of time. So you need to think of some examples of some functions that I can replace t with, whose output is still 0 when t is 0, and whose output is still 1 when t is 1, like t squared. T squared, think about that. Plug in t equals 0, 0 squared is 0. Plug in t equals 1, 1 squared is 1. This is a function, t squared, that still increases in value from 0 to 1 as t increases in value from 0 to 1. I also have to do it here. Replace the b with b squared. Let's see what happens when we look at this motion. We still start at the same point, 2, -1, just like we should. It's still along a straight line, even though we replace the t with t squared. It's still ending at the same point, -1, 3. But there is something different about it. What's different about this motion? It's starting slow and speeding up. It's not at a constant speed. There are infinitely many choices I can make here. T cubed works. Change that to a b cubed. It must be different than the last one. It is different. It starts even slower and ends even faster, which it's got to if it's going to still start at the same point and end at the same point in the same amount of time. If it starts slower, it's got to ultimately go faster. It can be even more extreme. T to the 10th power, for example. Change this to a b to the 10th power. Now this is barely going to move at first. Then all of a sudden it's going to move really fast. I would encourage you, before watching the next video, to think about why this is happening. Why does changing the input to the C function to being, for example, t squared or t cubed or t to the 10th power cause this motion to start at the same point, end at the same point, over the same interval of time from 0 to 1, but cause the motion to go slow to fast and get more and more extreme in terms of how slow it goes at the beginning and how fast it goes at the end as the power gets higher and higher. Try t to the 20th. It gets more and more extreme. Think about that before you watch the next video. Why is that happening? And it's moving so fast at the end that it doesn't even plot the last bit, but it does go to the right point at the end. Let me also entice you to think about what would happen. Well, I'll show you what will happen if I do this. If I replace t in both spots with 1 minus t or 1 minus b here. I'll show you what happens, and I would encourage you to think about why this is happening. This is actually not an answer to this example because it's going to go in the wrong direction. But that's kind of cool. Think about why that happens. But I'll end the video here just by replacing t with t squared in both spots as our thing that we'll start with in the next video. Whoops. T squared. Okay, see you in the next video.